okay?
It's okay. It's okay. We can start without me.
Yeah, so that means because Professor Zhang have the technical issue, so let me have a quick opening. So thank you for everyone to join this section. And then this section is cancer research and the new direction in Taiwan. And we have 3 presenters in this section. So the first one will from the Dr. Liu's lab. I believe it's Liu Ziqi, right? So if you are ready, you can start your presentation now.
All right, thank you, Chair. So let me share my laptop. So can everyone see my PowerPoint?
Yes.
All right, thank you. All right, so first, it's really a great honor to be here. And my name is Ziqi Liu, and my advisor is Dr. Professor Liu Qijie. And today I will be our presenter to talk about our latest research, and which the title is Identifying Important Risk Factors in Age Subgroups for Predicting Breast Cancer Based on Mammography Questionnaire Using Machine Learning Algorithms. And in today, this is our table of contents. So the first part, I will briefly introduce about some background about the breast cancer and some ideas and our motivations and why we're doing this research. And then we'll talk about some of the machine learning model we're going to use. And today, this will be our main focus would be the Sharpe value. So in our study, this time we use the Sharpe value to help us to explain the model to provide some more extra information that is more interpreted for our predicted outcome for like the breast cancer results. And so we have going to talk about workflow, and then we'll have to take a look at our data set we use for our modeling. And of course, I guess this would be today's most interesting part would be our results. So we will have some plots. Let's use the gradient from the Sharpe packages, and we can see how this information can help for some breast cancer studies. All right, so let's start it. Okay, so first, we understand that the cancer is really what's a puzzling disease around the world, and we already know there are a lot of studies that conduct into this field, and also there is a lot of study that tells us that the most common type of cancer incidence of women is globally is the breast cancers. So based on this literature, you can already know that breast cancer is kind of important issues around the world. And of course, there are a lot of studies that already tell us when they're suggesting that if for early detections of the breast cancer and along with some proper treatments, it can decrease the mortality rate and overall increase the survivability. And so here we can understand that for breast cancer, and from a public health point of view, the prevention and diagnosis to early detect whether a patient have a potential of getting the breast cancer will be pretty important in these scenarios. And then in Taiwan, here is the plot, and we gather from the Ministry of Health and Welfare. And I apologize for the translations, but I translate some of the important words in these slides. So first, as you can see in this plot, this is the latest report from our government, and it's about in 2021. And we can see here the top cancer in the Taiwan between the age of 45 to 54 is the breast cancer, which is the top one. So you can see that the high risk groups of people getting breast cancer is actually 45 to 54. And with the plot, you can understand, yes, when the age range is increasing, the breast cancer's risk will be kind of lower. But anyways, you can understand that most of the population is between these age groups. So in our study, the first we are going to try to focus is to making the models for predictions is the high risk population, which is the age between 45 and 54 in our study. And usually, I think it's same around the world that so for breast cancer kind of diagnosis, the most used diagnosis would be the mammography exam. And this is also includes the same in the Taiwan. And of course, we have another kind of the type that, or I can say is with tools that can help us to diagnose would be like a screening survey. So the screening survey is kind of a questionnaire-based surveys, and that will ask the patient that to fill up the survey, and we can have some ideas of some status of the patients currently, like their basic informations or something about their like lifestyle or their health status at the moment when they're filling the surveys. And of course, our data have some interesting is we're fortunate we can, in the hospital we are working with, they will ask the patients come to for the mammographic exam, will ask them to fill up a survey. And so with this, our data collected from the survey will have actual linkage to the exam result. So with this, we can see, we can use our features from the survey, then we can to study like the cause and effect between those what we call the risk factors, that how they may affect or impact the exam outcome. So here we can understand the interpretability is what we are looking for here. So what we're trying to do here is we want to provide extra more information that may help for like from public health, like for government or large clinical center, that they can provide more information that can be referenced, maybe could change or to improve their policies or some regulations, or just overall help the public to have more knowledge of like breast cancer and to overall decrease the mortality rate is what I'm looking for here. So to kind of sum up our introduction section, our core concept would be here is early detection for breast cancer. So which means we want to have some like models that can help us to predict, and with those prediction, we can maybe to increase the prevention rate and for diagnosis. And so here comes some problem here. So first, we understand in clinical kind of studies that features usually have complex interaction between each others, which means like the nonlinear relationship or like collinearity. So to tackle this, we use the machine learning model, which is a data-driven method that can have a better tolerance of the collinearity and can capture the nonlinear relationship better than our most used traditional methods, like such as logistic regressions. And there's another problem is usually in clinical features, sometimes the relationship is not linear. Of course, we wish it would be linear because it would be more easier to interpret. But however, that is really not the case in our real case scenario. For example, like for body mass index. So we understand that with higher body mass index indicate obesity, and which is not suggested, and which will and is more risk for the health for people. And on the other hand, for lower BMI, it is being too thin, and it's also not suggested for the, if a person is healthy or not. And if we plot the mortality rate or the risk ratio on a plot, we'll see we will be like a U shape, which the middle of the BMI values ranges will be the most lowest. So with this kind of characteristic of the features we have, so here remember I mentioned previously our age group would be 45 to 54. So we actually do a subgroup for the ages into two groups, which is 5 groups, 5 age each. So which would be 45 years old to 49 years old and 50 years old to 54 years old. And then will be another limitation will be made is where the machine learning models, the explainability will be limited sometimes. And this is where when we refer to the black box model. And like, for example, for example method, it is powerful, but sometimes the explainability will be limited. So this is why the reason we are going to use the sharply additive explanation to explain our outcome from the machine learning model. So now I'm going to talk about some of the machine model we're going to use. So like first, in our study, we use the XGBoost, and this is actually pretty popular right now, and a lot of clinical related studies have used the XGBoost. And for here I mentioned about the limited explainability, I was going to use random forest to explain more, since random forest is kind of more straightforward to understand. So here, we understand that random forest is an extension of decision tree. And we know it is an example method that utilizes the bagging method. So which for random forest algorithm, it will create lots of decision trees, and when the outcome is going to be predicted, it will utilize the majority voting. So here we will understand that with random forest models, there will be actually a 50 or even 100 even more decision trees. So when we have a prediction, we're going to ask another question is why or how the model predict this specific case as positive or negative. When we want to know why, at this situation, the random forest will be limited since it is not practical for us to look at all the 50, even 100 of decision trees. So with this, we can more understand why sometimes there need a method for us to increase the explainability of a machine learning models. So this is why we come for the 8 is the sharp value. And today, because due to the time, I'm not going to introduce sharp more mathematically, but rather I will more pay attention to the concept of the sharp value. All right, so here, so the sharp value is actually an extension of the sharply value from the cooperative game theory. So to make it simple, there is a plot and we can explain more detail. So first, in the game theory, there will be like, for example, will be 3 players. So what sharply value is going to do is each collaboration between each players will have different outcomes, or in this case will be like a different prize money, or how we say the playoff. So with these different combinations along with their corresponding outcomes, we can use the sharply value to estimate each player's contributions to the overall payoff of the money. So this is actually the basic concept of what sharply value is trying to do. So in other words, each player in this particular game and with different combination or we say like collaboration between players will lead to different outcome. And with this outcome, we can estimate how each single player's contribution to the actual outcome. So with this concept in mind, when it comes to explain a machine learning model with the sharp value, we just simply change something, and then we're going to turn into a sharp value. So first, for the player in sharp value, we just need to change our player to our features. And as the prize money here, when we're going to explain our machine learning model, the prize money will just be a predicted outcome from our models. So, and basically the sharp value is using the same concept. So we just imagine now we are going to try to see how each features contribute to the actually predicted outcome. And of course, for sharp value, there is a lot of different types. So like if you ever heard like the deep sharp and like tree sharp and kernel sharp. And here in our study, we're going to use the kernel sharp, and which is a method that also include the line. And we will use a linear function to approximate the contribution of each features. And for more mathematically and a proof, you can refer to the original study. And here I'm only going to point out an important equation here because this will relate it to our results, which will be a local accuracy. So as I mentioned, sharp is actually an approximation of the predicted outcome and to check how each features contribute to our outcome. So with the sharp values definition, this f of x will be our actual model's output, and we will the result will be almost equally to our explained model here, the outcome. And the phi here is actually the sharp value of each features. And here another thing we need to pay attention is to the phi 0. So as I told before, for the game theory, we have different collaboration of the possible combination of the players. So there is also a combination, it's like here, is there is no players will have an outcome. So when for machine learning, this will be what we call the naive prediction, which is when we want to predict an outcome and no features will present, and the normally will be our naive outcome. And so for sharp value, the naive outcome would be the expected value of our models. So for regression will be the mean of our target variable. And for classification will be two cases, will be the actual percentage of our one of either the positive class or the negative class. All right, so here we'll talk more about when we look at our results. And now this is our workflow. So basically, in our study, we will collect the data first. And of course, we told about it, our data have a direct linkage to our survey and the exam result. So after we collect these results and this data, we will do a data preprocessing process. And here is just like we will check for the missing value and we'll drop those missing value. And we also will perform a quality check. So like, for example, the illogical time. So basically, like in our data, we have the features like for the age of first childbirth. So ideally, when a woman can give a birth to a child, she is already have begin the main arc. So, but sometimes since this is a survey that filled by the patients, so sometimes they will wrongly fill the survey. So we also perform a quality check for these kind of issues, and we will address these issues or like dropping all these illogical time values samples. All right, so after our data is cleaned, and we also will have our model constructions. And so these are the normal basic procedures that is commonly seen in machine learning modeling. So we do have 80% for training, and we split to 20% for testing. And we also apply a 5-fold cross validation for our hyperparameter tuning for our use method. And here you can see the lasso is actually the logistic regression applied with the lasso regularization as our benchmark. And another problem is our data actually have some imbalance issues. So we treat the imbalance issue by we adjust the threshold for the actual outcome to deal with the imbalance issues. And then when we finish our modeling process, we will find the best performed model, and then we will use the best performed model as our base model, and then we will apply the sharp value to explain the outcome from our best model, which with sharp value, we're going to have the information of like feature rankings and the individual case explanations. All right, so now let's do our data. So these are the 16 features we are going to use when building our machine learning models. And here I present our target variable Y in different subgroups here. And as you can see, as I mentioned, you can see here do have imbalance issues here. All right. Now I think the most interesting part will be here, results. So first, here, 3 tables present our machine learning models results. So you can see in both age 45 to 49 and 50 and 54 groups, random forest is our most desirable method. And here I'm not going to use the term the best model, rather I will use the most reasonable, since we have to frankly say, because our data structure is a survey based, so sometimes the structures inside the data is not really clear. So, and a lot of study that utilize a survey kind in the public health related studies, usually the AUC around 60 or 65 or maybe higher to maybe 70 is usually pretty commonly. So here we can say our result is reasonable. And then we can see with table 3, we take our RF model here can do direct comparison in different age subgroups. We can see interesting with similar AUC performance. We can see that in age 50 and 54, the sensitivity is better than our age group in 45 to 49. So which indicates with these age groups, our model can capture the patients with potential breast cancer positive more better than in the 45 and 49 groups. All right, so here, if we remember our workflow, our RF will be our models and will be utilized with the sharp value for a further explanation for our predicted outcome from the random forest model. So here is a first plot we can get from the shard package. So these are directed get from the Python package they created from the authors. They are kindly allowed to provide these packages for us to use. So with this plot, there's a lot of information they can tell us. So first, we want to look at here. Here are the features, and with the shard plot we take out from the Python package, it will automatically rank the features. So which the most important feature would be on the top one, and then the least important features, the relatively least important features will be on the last one. So next, here we can see here is a feature value. So this feature value is not the shard value. This feature value means the exactly value of the features for each samples. For example, here we can look at the breast self-examination. In our breast self-examination features, we have 3 class code, which will be 0 represent a breast self-exam negative, and 1 represent never breast self-exam, and 2 mess or pain tenderness. So these color indicates the values when we input to the models. So as this part here, you can see the x-axis will be the shard value itself. So this plot will tell us is we can see here. We can see most of the colors are red to the right, which means these are positive effect, which means for these features, when the models predicted positive class, these features with a larger value will impact our overall prediction outcome positively more. And with lower value, it will impact our predicted outcome less. So this plot can give us an overall summary of how each samples in our features impact to our predicted outcome. And there is a pretty important reminder. These results are actually the testing data, which means in our data around, if I'm not mistaken, would be around 1,000 samples, I believe. So these are actually those 1,000 samples outcomes from our trained models and the shard value of those 1,000 samples. So do not be confused. This is not the values from the trained model. It is from the testing model. All right. So and here is another plot for the 50 and to the 54 age group. We can take a look at here. And it's the how to read this plot is always is the same. All right. So next, with this sharply summary plot, we can overall to understand how each feature's values is positively affect or negative impact our outcome. But sometimes we just want to get the grasp of the overall the ranking of the features. So there's another way to present is we can just simply we take the mean and absolute shard values of each features. So these two plots are actually the mean values of these shard values and then just average. And we'll get this plot. As you can see in both different groups, we can see the features actually impact our outcome differently. So like in IHMC is all in the top rank 1 in our both age groups. But like for the second and third would be quite differently. Like so breast examination would be in the early age, the first age group, but like in parity would be the second, the 50 and 54 age groups. All right, so here, from here, these plots is for overall, we use this plot, the information tell us the overall how our models predict the outcomes. But sometimes when we talk to the more personalized medicine or personalized diagnosis, we want to learn more how each features that will impact each patients. We can use another plot. It's called the waterfall plot. And oops, I forget to talk about this one. And so in this slide, we just can combine these average points to get a overall average of the important features from both groups. All right, so next, for an individual case explanation, Sharp can also provide this explanation. But here we need to pay attention to our datum point, or what I'm going to say is another word is would be our reference point. So if you are familiar with how actually an algorithm works for classification problem, you can understand that for a classification problem, the models usually output two columns of result, which is whether this case or the likelihood of this case is going to be positive, and the likelihood of this case is going to be negative. And of course, for clinical study, we usually focus more on the positive case. So we usually just take the positive case one. So with sharp value, we need to be careful of our datum points. Since if we remember this equation here, so for the positive case, this will be the percentage of our input data when we train the model. So here you can see our positive case is around 0.196% of the data. This will be our starting point. So how to read this plot? First, as I said, we adjust the threshold since our model have embedded issues. So here, this is a actual outcome for our model is here. F of x would be 0.356. And with the adjusted threshold, when the threshold is the likelihood value is greater and equal than the 0.213, then the case will be regarded as the positive. So here, this is a positive case. And now, next, we're going to start from here. So these values here are the actual features value of a sample. So which this is a sample A will be like a patient. So his her breast cell examination result will be 2, and education level will be 4. So and so on. And then these color bar are the exact sharp values of each features. So we can see here when the model without any features make a naive predictions, it will be a negative case if we can compare our threshold. And then when we add more features to it, we can see how the value is changed toward to the final outcome. So you can see here with the duration of outcome, they use a little bit of negative impact and then a positive impact. And then we have more positive impact and negative, and just like add it up. And to the end, we could see in this plot, this patient be predicted as a positive case is because her breast self-examination is 2 and her education level is 4. Since these two features with this value relatively is impact more. So with this individual case, we can understand for this patient specific, breast self-examination 2 and education level 4 is what we need to look for. And with same concept, for the negative case, we can also use this plot to understand how each features affect our final outcome. So like in this example, the threshold would be the 0.787 for the negative case. And we also can see how each features values and its corresponding sharp values impact our final outcome.
Excuse me, Chi, could you please closing your presentation with 1 minute? Thank you.
Oh yeah, sorry, sorry. And actually, I just finished explaining the plan. So, all right. So in conclusions, so as I said before, we have our main point is for early detection and a model, and for interpretive for our machine learning model to provide more information that may help like the facilities or official to maybe improve their policy or like some regulations. So here we demonstrate how the application of sharp value that may help our studies in like some cancer and breast cancer studies. And also we demonstrate we can provide extra information for breast cancer diagnosis. So like for feature rankings and our individuals explanation plot. And also this is a different approach for the personalized medicines. And of course, for our future study, we want to explore more potential usage of machine learning and the sharp value for the explainability of machine learning in clinical related studies. And so I do apologize for the time here, and I appreciate your attention today. And I really thank you for everyone to have let you have this chance to share our studies. And so thank you. And back for the chair.
Sir, we cannot hear you. Can you open your microphone? Professor Chicheng, we cannot hear you. Can you switch on your microphone?
Okay. Thank you for your
Thank you.
interesting and very detailed information about the breast cancer issue. I think the following will be the most important part about the question and section. And then I will want to create now country right to the issue. I will following clinical validation will be for my question. And thank you for your question. Okay, and I would like the speaker, Professor here. As with told and the gastric the pony composition.
Excuse me, it's my turn now. Sorry,
Now I think
signal is
the
not very
Professor
stable.
Chicheng has trouble about internet connection. I think it's your turn.
So it's my turn, right?
You, thank you.
Okay. I'm sorry, can everybody see my screen?
Yes.
We can see.
Thank you. Hello, everyone. My name is Sihan Chen. I'm very happy here to make a brief introduction for everybody. This presentation is talk about a feature selection method, rank aggregation-based method. And we use the proposed method to gastric cancer recurrence problem. And my name is San Chen. I'm now an associate professor in Department of Industry and Engineering and in Minzhi University in Taiwan. And Dr. Zhang here is my partner of this research. And we did this research together. And three primary messages you will take home. The first one is to access the information about the gastric cancer in Taiwan. We will have a short one-page slides and to show the trend of the cancer. And the second one is to introduce the proposed rank aggregation-based feature selection method for you, which is able to predict the recurrency and identify the robotic risk factor for you. And the final is to demonstrate the analysis result for patients with gastric cancer recurrence. Okay, let me brief talk about the gastric cancer in Taiwan. And here is the trend of the top 10 cancer death rate in Taiwan. The top 10 cancer in Taiwan is lung cancer, liver cancer, colorectal cancer, and so forth. And you can see the gastric cancer is ranked in fourth, about 2000. But the ranking goes down from fourth to about 8 in near 5 years. It's a good news. So the trend of the gastric cancer is decreasing. And we also know the median age of the death rate for the kind of cancer is about 16 years old. So we do this research with 3 goals. We analyze the data set from gastric recurrence phenomena of patients to quantify the clinical feature and the development of predictive model. And we also can identify the relevant risk feature. And the difficulty for this research have two points. The first one is the data set has a middle level class imbalance problem. And second one is the iterative risk factor fluctuate among different methods. So we are trying to build up a method which can handle imbalance problem, and also we can get a robust risk factor list. And we also hope that the method can automatically select the risk factor, and which can also predict the result with fewer features. And the advantage of the feature selection will be shown in here. First one is to remove irrelevant feature. And it possibly can increase the performance of the model. And the feature selection make the model training faster. And we also can build a model very easier and easier to understand and easier to debug. So based on those advantages, we trying to build up another kind of feature selection method like this flowchart. The method is called hybrid committed method for feature selection and modeling. First one, we input the data set, and we divide the data set with a specific percentage, for example, 60% or 17%, and divided it into the training data and the testing data. And the testing data will be processed by so many preprocessed technology, for example, upsampling, for example, missing data, preprocessing, or etc. Then the preprocessed data was built up a model by a specific classifier. Then the classifier hyperparameter was tuned by K4 class validation. And with the K4 class validation method, we will get a best model. In this best model, it will have a good hyperparameter to be chosen. Then we use different kind of feature ranker to rank the feature importance individually. So for the first feature ranker, we have a list of feature importance. Second one, we also have another feature important list. And the adult feature ranker, we also have adult feature ranking. Those information are then aggregated by a method called rank aggregation, such that we can get a selected feature importance ranking. So our original data was feature was filtered out by this information and build up the classifier again. And the hyperparameter was tuned by another K4 class validation. And in this stage, we got the final model. So with the final model, we convert the test data in this stage and do the totally similar preprocess technology for the testing data. And then the data was converted into the final model to get the predicted result. And another question is that what kind of feature ranker we select. In this research, we select 5 feature ranker. The first one is variance-based feature importance measure, and another one is ICE-based measure, and model-specific measure. And we also have permutation-based feature selection measure. And finally, we have Shapley-based feature importance. Then the 5 feature ranker was aggregated by another method called rank aggregation. Rank aggregation is an optimization problem. The objective function of this method is to find out a delta star, which can minimize the total distance between delta star and the LI. And let's briefly talk about this equation. It's the objective function of the aggregation. You can see here the delta means the candidate feature ranking, and the LI means the feature ranking suggested by ICE feature ranker. So we will compare the ongoing solution between the ICE feature ranking with a distance called Spearman footloop distance. And we also can give some weighted for different kind of feature ranking. In this research, we set up equally weight for each kind of feature ranking. Then the N means we have how many feature ranker we have. In this research, we have 5 feature ranker, so N is equal to 5. Then those values will take the argument minimum for optimize delta. With the argument minimum, we have a solution called delta star, which can minimize the Spearman footloop distance between the candidate data with different kind of feature ranker. So let's see the analyzed result for patients with gastric cancer. Our data set has about 2,500 records, which was provided by Taiwan's hospitals. And the cases with gastric cancer and then suffer from first recurrence is about 400 cases, which was less than that with not suffer from the recurrence, about 200 cases. And we correct 17 dependent variable for the data set and 1 dependent variable in the data set. The dependent variable means recurrence or not. 1 means recurrence. 0 means no recurrence happen. And the data set has a class imbalance problem. The percentage is about 1 versus 4.73. And our data set was randomly divided by 60% with 40% with respect to training data and tested data. And let's first see a quickly spot checking result. We use different kind of classifier to build up the relationship between our dependent variable and independent variable. And you can see that for the less row, the ranger has the most development potential compared to other classifier, because we can get a relative high accuracy and relative high AUC. And the most important is that the sensitivity and the specificity are relative balanced. So this method have a relative higher balanced accuracy value. And what is ranger? Ranger is a C++ implementation of random forest. So this method is a kind of is very similar to random forest, but this method can train the model faster because it was based on C++ implementation. Then we also can see the feature importance calculation for the ranger from different kind of method. As we say, variance-based, ICE-based, and so forth. We can see some fluctuate between different feature importance ranker. For example, we can see every method have constant optimum for the top one feature is combined stage. But for second top two feature, variance-based and ICE-based method say that SSF5 LVI is the top two feature. And the model-based say regional reffing north positive was the top second. And the permutation-based maze say SSF3 was the second place. And the Shepherd-based say regional reffing north positive. That's why we caught the fluctuation. Then a kind of method called mean aggregation, which can take the average value between different kind of feature ranker. Then finally, it can suggest a integrate feature importance ranking. But our method called rank aggregation, we have different rank compared to the mean aggregation. But the first one still the combined stage. And the second one is regional reffing node positive. The third one is chemistry zeotropic. We also did some information and experiments about how many features we want to extract. As you can see in this figure, when we train a ranger with 4 features, top 4 features, the AUC is about 0.779. And when we increase the feature number to 8, the AUC remain 0.79. But when we add more feature on this method, the AUC start to decrease. So maybe the top 5 feature, extract the top 5 feature, top 8 feature will be the best. Then we also do some comparison study on testing data. We compare with some individual classifier with ranger and the ranger with feature selection using mean aggregation and the ranger with feature selection with proposed method. As you can see, GLM and LMT have the highest prediction accuracy, which can reach about 76. But you can see their sensitivity was very low, very low. And the prediction accuracy of R part and the conditional inference tree and the C50 is slightly lower than GLM and LTM. But their sensitivity and specificity was relative balance, but it is not good enough. And you can see the Ranger is more outstanding, which have balance accuracy highest
I think we have some connection problem, right?
Yeah.
Yes.
I'm sorry, internet was
Okay,
not very
okay.
stable.
I
Okay.
think the interrupt for at this moment. I would like to make a. Can you hear me?
Yes, I'm sorry
Okay.
for network unstable.
Okay. Actually, I think
Yeah.
due to the time, I think this study is develop a new way to select the important feature based on the aggregation. Actually, we have talked to this result with our clinical data, and they all confirm that this result can help interpret new risk better for cancer recurrency. Okay. I would like to take this opportunity to you may have 1 minute conclusion of your presentation. It's possible. I think you are back now.
Okay, the
Okay.
conclusion is that we build up a method which is application with the prediction of gastric cancer recurrence. But I still think it is still a top problem and top challenge for this method. So this performance also need to be improved. And another conclusion is that Ranger use all feature for prediction is not very good. But when we select the important features, we can achieve better performance for balance prediction. And we finally find that the top 8 features are in here. For example, combined stage, regional riffing node positive, and chemotherapy, and so forth. And thank you for everybody, and thank for the chair to introduce and make some material for everybody. Thank you.
Okay, thank you, Professor Chen, for your interesting and very helpful clinical contribution. Okay, the next one, I would like to introduce our last speaker from National Yangming Jiao Tong University, Professor Deng Yiru. Sorry. Okay. His topic will focus on the federated learning for predicted second primary cancer, especially for lung cancer. I think it's a very critical and important issue. And she will focus on the survivor and collect the data from multi-institute study. Welcome, Professor Yiru Zheng.
Yeah, I'm sorry that let me briefly introduce this study and also introduce the team member from our lab. It's Ruifu. It's Hong Ruifu. He will present the research topic for everyone. So you can share your screen if you are ready. Thank you.
Okay. Wait a minute.
Yeah. So when Refu is sharing his screen, this study it's about federal learning. So because the privacy issue, it's kind of one of the important issue when you aggregate data from different institutions. So that's the reason why we perform this study. So I think Refu is ready.
Okay, so today I'm going to introduce the topic about the privacy issues in the machine learning. So in our research, we have two goals. One is to predict second primary cancer for lung cancer survivors, and the other is to use privacy preserving methods to break through the barrier of the current learning method. So as we can see in 2020, according to WHO statistic, the lung cancer is the second most diagnosed cancer, and the death toll was also the highest in the worldwide. So with the growing number of lung cancer, the chance of patient diagnosed with second primary cancer also getting higher. So what is the second primary cancer? For example, if a patient who was recovered from the first primary cancer of lung cancer, after a few months or years, the patient was diagnosed with another new cancer. And this new cancer doesn't belong to the metastasis of the first primary cancer. Then this new cancer will be regarded as the second primary cancer. So if we can build a model to predict which patient has higher risk of getting second primary cancer, we can use this model to improve the treatment outcome. So in previous studies, some researchers has used the centralized learning or localized learning to build a model and make a prediction. But both methods have some shortcoming and limitation. Take the localized learning as an example. Each hospital needs to use their own local data to build a model, but some hospital has the small data set problem. This may make the model performance worse. So with this problem, the centralized learning was introduced. As we can see, the centralized learning can collect the data from different hospitals. So if we can build a model with larger data set, the model can learn different features from different hospitals, which may improve the model performance in some degree. But with the rise of the data privacy issues, some countries have established strict regulations, such as HIPAA and GDPR, which lay down to restrict the data transmission and preservation. So that means the centralized learning may not collect the data from different hospitals in certain situations. To solve this, to solve the data privacy issues, a few privacy preserving methods were introduced, such as the federated learning and transfer learning. So next, we are going to take a look at the federated learning process. At the beginning, each hospital will receive an initial model parameters from a central server. And every hospital will start training their own model using their local training data. After training the model parameters of each hospital are transferred to the central server. Then the central server will aggregate all the model parameters to come up with a new model. And this new model will be sent back to each hospital. And the aggregation method we use is the Fed average. The Fed average will calculate the means of each hospital model parameters. Okay, so next we are going to talk about the transfer learning process. In transfer learning, the biggest hospital with the biggest data set will use to build the pre-trained model. And the other hospital then use their own local data set to fine-tune the pre-trained model. Then they can come up with their own fine-tuned model. And in our experiment, we use 8 hospitals from Taiwan. And the data set include the clinical data and demographic data. In our training strategy, we compare 4 different learning methods that were mentioned above, including localized learning, centralized learning, transfer learning, and federated learning. And all the training methods were simulated over 60 times. And the evaluation metrics we use is the AUROC score. And next, we can take a look at our experiment results. In most hospitals, the federated learning can outperform localized learning and reach similar performance to centralized learning. But in the hospital 6 and 8, we can find that after they join into the federated learning, the performance become worse compared to the localized learning. We suppose this may caused by the data heterogeneity problem, which means the heterogeneity problem, data heterogeneity problem means that the data distribution of this hospital were different from others. So the performance might be worse. So to solve the data heterogeneity problem, we plan to implement the model personalization and client selection method to trying to reduce the negative impact of the heterogeneity problem. And at the end, we can find that the privacy preserving method can not only reduce the risk of the data security, but also maintain the model performance. So this is my presentation. So any question?
Okay, open any comment or question? I would like to invite Professor Zheng Yiru. Do you have any question about this study?
Because I'm part of the study, so of course I don't have any question. But I want to emphasize that we have a really good privilege that can get all the data to perform the step. We call that centralized learning. But in a lot of settings, we cannot have this kind of privilege to get all the data from all the different hospitals, right? So probably federal learning it's a good way to solve this question, but still we need to solve the issue of the heterogeneity between the hospital. For example, from the different if the data from teaching hospital, probably the patient population is different from the small hospital, like a local hospital, etc. So this is our next step, and then hopefully we can solve this question with some personalized adjustment. Yeah, it's just quick summary. It's a quick summary of this research. Thank you. So
in internet synchron with inter and okay. You hear me?
Professor Zhang, I think the internet is kind of not stable.
I share this you
Professor Chichik, we cannot hear you properly.
Yeah, the internet is not really stable, so we cannot hear you.
Yeah, maybe we can text. Yeah.
Okay. Oh.
Maybe we can finish our session because there is no left to the speaker, right?
Yeah, so probably yeah. So first of all, thanks for all the presenters that joined this section to share the up-to-date research result. And I would like to thank the chair of this section and also the staff from the conference to make this section happen. So finally, I would like to ask if there's any additional question before we close this section. No? So if not, so probably I can announce that this session is closed, and then thank you very much. Thank you.
Thank you.